When a massive, unpredicted surge in network traffic hits a modern application, the underlying infrastructure has to scale in milliseconds to keep the system online. As of 2026, the sticker prices for basic compute virtual machines on AWS and GCP are almost identical. A standard general-purpose instance on either provider is typically separated by only fractions of a cent per hour. These identical line graphs track the exact same traffic spike, yet routing this surge generates drastically different monthly bills. This gap stems from specific architectural choices regarding how each provider bills execution time, handles concurrent requests, and charges for idle resources. To understand exactly what you are paying for, we are going to deconstruct the modern compute stack, examining serverless functions, containers, and managed Kubernetes. We will expose the exact mechanical differences that silently inflate or discount your cloud budget based purely on your traffic patterns. Relying on market share to dictate your infrastructure strategy, rather than workload behavior, will rapidly deplete an organization's funding runway. We start at the function as a service layer. Function as a service, or FaaS, is a model where developers deploy individual blocks of code, and the cloud provider manages all underlying server allocation and scaling automatically. Because these functions only run when triggered, they are susceptible to cold starts. A cold start is the physical latency penalty incurred when the cloud provider must allocate a new container, initialize the runtime environment, and load your code before it can process a request. AWS Lambda utilizes a strict one-to-one concurrency model. This means that if your system receives 100 simultaneous incoming requests, AWS Lambda spins up exactly 100 distinct isolated execution environments to handle them. This approach ensures that every request has its own dedicated pool of CPU and memory, providing absolute predictability. However, it forces multiple cold start delays during traffic spikes, as every user needs a fresh container. Google Cloud Functions uses a multiplexed model instead. A single GCP container handles multiple simultaneous requests, defaulting to 80 concurrent executions. For code that is I/O bound, meaning the processor is sitting idle while waiting for a database record or an API response, this multiplexed model is highly efficient. It processes dozens of other incoming requests during those wait times, which lowers both your memory consumption and the total number of containers being provisioned. But the financial mechanics of how these platforms bill for execution time add another layer of complexity. AWS Lambda calculates your compute duration using precise 1 millisecond increments. This chart comparing a 15 millisecond execution time reveals a hidden cost multiplier on the Google side. While the AWS bar stops at 15 milliseconds, Google Cloud Functions rounds every execution time up to the nearest 100 milliseconds. If your microservice is optimized to respond in 15 milliseconds, AWS charges you for 15. Google rounds up and charges you for 100, effectively imposing a massive rounding tax on highly efficient codebases. GCP's platform relies entirely on its 80-to-1 concurrency model, sharing those rounded 100 millisecond billing blocks across multiple simultaneous requests to offset this structural pricing penalty. AWS Lambda is the financially superior choice for ultra-fast, computationally heavy, and highly isolated synchronous execution. GCP is structurally superior for data fetching pipelines prone to high wait times. When workloads outgrow simple functions but don't require the massive management burden of a full Kubernetes cluster, serverless containers provide a middle ground. On this quadrant chart, Google Cloud Run sits in the unpredictable traffic category. Using an active request billing model, charges for CPU and memory pause when request processing finishes. It scales to absolute zero when traffic stops, ensuring you never pay for idle time. Cloud Run initializes full web servers in seconds, providing a responsive environment for sporadic traffic. In contrast, AWS Fargate uses a continuous resource consumption model. You are billed for vCPU and memory from container start to termination, regardless of request volume. Fargate also has slower spin-up times. This is because it must attach a dedicated elastic network interface to a virtual private cloud, an isolated private network, before the container can initialize, creating a latency penalty that makes it poorly suited for scale-to-zero architectures. While Cloud Run's model saves capital for startups with sporadic traffic, Fargate's flat compute rates often yield a lower total cost of ownership for heavy 24/7 enterprise services that maintain high CPU utilization around the clock. At the peak of the compute stack is managed Kubernetes. Both Amazon EKS and Google GKE manage the complex Kubernetes control plane for you, leaving your team to focus on the underlying worker nodes. Operating these clusters involves two significant hidden costs, beginning with control plane management fees. This comparison matrix highlights an entry-level difference. AWS EKS imposes a strict 10 cents per hour flat fee for every cluster control plane. For an organization running 11 clusters, that's over $700 a month before provisioning your first server. GCP strategically counters this with a free tier that waives the control plane cost for your first cluster, significantly lowering the barrier for smaller teams or sandbox environments. The second hidden cost driver is persistent storage. On the matrix, notice the storage substrate gap. AWS Elastic Block Store starts at 10 cents per gigabyte per month, while Google Persistent Disks start at just 4 cents per gigabyte. For data-heavy applications requiring terabytes of replicated storage, GKE's underlying hardware offers a massive cost reduction at scale. Finally, we have to look at how quickly these clusters respond to sudden traffic spikes, especially for hardware-intensive tasks like AI model training. In 2026, Google updated GKE to allow concurrent node pool creation. By provisioning multiple groups of servers simultaneously, they reduced autoscaling latency by up to 85% compared to older sequential models. AWS responded with EKS Auto Mode. This system completely abstracts the infrastructure by automatically mapping nodes to the specific requirements of your application pods, terminating unused instances and consolidating workloads without manual intervention. GKE frequently wins on baseline storage costs and scaling speed, while EKS provides a more automated, hands-off experience for sprawling enterprise environments that want the cloud provider to manage the entire infrastructure lifecycle. Total cost of ownership is a direct function of how well a provider's billing architecture aligns with the specific behavior of your code. If you are building a data-heavy pipeline with unpredictable traffic and high I/O wait times, then Google Cloud Platform is the logical choice. The financial protection of Cloud Run's active billing, the high concurrency of cloud functions, and GKE's cheaper storage substrates provide the most efficient framework for this workload type. However, if you are running a continuous enterprise service with steady, high-volume traffic and millisecond-optimized code that requires strict network isolation, then AWS is the superior platform. Fargate's flat compute rates and Lambda's 1 millisecond billing precision deliver a significantly lower cost when running at maximum sustained capacity. Successful cloud strategy requires calibrating your provider choice to your exact traffic footprint. Misaligning your application's architecture with the underlying billing ledger is the single most expensive mistake in modern cloud computing.